hi everyone, I'm Barney, and this is my colleague Fi. I'm a senior data science manager in the sports data science team at DraftKings, and Fi is a lead data science engineer. Predominantly, we look after basketball, and I also look after football as well. But yeah, today we're going to talk to you about how to maybe make money betting on the NBA with rocket science. So just to kind of quickly go through what the agenda is. So firstly, what we do, and then we're going to talk about the rocket science, and then Fi is going to talk to us about how we're using that rocket science specifically for the NBA, and how we're utilizing Databricks as well. And then finally, how to make money, the good stuff. Yeah, to start with, we'll talk about who we are. So myself and Fi, we are a part of the sports data science team within the sports intelligence unit at DraftKings. And primarily our responsibility is to produce the odds that are on the DraftKings website using our sports models. We do this by building fairly complex Monte Carlo simulation-based pricing engines. Very often, these pricing engines will have several machine learning models embedded within them to handle certain aspects of the sport in question. So for basketball, we'd have maybe a model that handles the possession outcome, so what the score of the possession would be, and we'd also have a model that would handle the possession length, the length of the possession as well as various others. And using these engines, we can price various markets or produce the probabilities of certain events happening which become markets. So for instance, the final score of the game, the time of the next touchdown in NFL, or the next team to score a 3-pointer in the NBA. And then at the end of it all, we basically get what we have in the screenshot here, a bunch of odds on site that a customer can bet on. So what we're going to talk about today is our mission to produce in-house player props, basically. And at the end of 2022, we were given a problem to solve, and that was our team was asked to produce a basketball model that is capable of producing NBA player prop markets. So if you don't know what that is basically a market where you can bet on over, under a player to achieve a certain number of a certain stat. So that could be Steph Curry to score over 28.5 points, and we need to produce reasonable probabilities for that occurring. So the way we want to do this is make our basketball model player-centric. And that means that it understands the value and impact of all the players that are involved at any point in the game. And at the time, our model it didn't understand players at all. It was a very kind of team-centric model. It was quite a good model, I might add, but it wasn't player-centric at all. And when we first started the project as a team, we were really only beginning our journey into adopting proper MLOps practices. And as such, we wanted to utilize Databricks to produce robust feature and model pipelines, as well as monitor the quality of our models automatically. So before we get into the basketball specific aspects of this, we first need to talk about the rocket science. And that comes in the form of Kalman filters. Fi will talk later on about how we're using those for NBA, but this is, to start with, we're actually going to talk about how they actually work and what they are and where they're used. So yeah, we've got a few complicated looking equations there, but Kalman filters are an algorithm that allows you to measure an object through a series of measurements and estimate an unknown variable. And what the formula at the top there is basically telling us that you'll have for any object, you'll have an expectation of how much that's worth effectively. You'll have a measurement, and the difference between those, weighted by something called the Kalman gain, is what you bake into your prior estimate effectively, and that becomes your new estimate. The Kalman gain is basically how much uncertainty is in how much of the measurement you're going to take forward into the new rating. And that is mostly determined by the proportion of the uncertainty in the object, your prior estimate of the object, as well as the uncertainty in the measurement of that object. And then finally, the final thing to take account of is the uncertainty in the object itself. So every time you have an observation of the object, whatever it is, we also update the uncertainty in it. So obviously the more measurements you have of something, the more certain you become about how much it's worth. And this is what this covariance update formula here is. It basically tells you how much more certainty you gain with every single measurement you have. So a few typical applications of Kalman filters are numerous. Can be used in autopilot, portfolio optimization, financial time series prediction, GPS, rocket science, obviously, and many more. And this is a testament to how versatile Kalman filters are. It's going to work.
It should work.
Play. Oh, I'm playing. Cool. So this is a DraftKings groundbreaking rocket game. The idea is the rocket keeps going up. If you basically make more money, the rocket goes up, and you basically have to jump out the rocket before it blows up, or you lose your money. It's the idea. It's the rocket game. It doesn't actually use rocket science though. And neither do sports typically. But that's exactly what we've done in this case with the NBA. And it's actually fairly easy. So let me illustrate that with an example. So the Olympics is around the corner, so this is a topical example. So here we have Usain Bolt. And if you didn't know, somehow he is the fastest person to run 100 meters ever. And here are his 100-meter times plotted over the course of his career, including his 9.58 second world record, and everything else he's run in the final. I've actually extracted out some of his times that weren't run in finals, and the reason for that is because Usain Bolt didn't typically run at full 100% during non-finals because he didn't really have to. So the purpose of kind of measuring his ability, you probably just want to take those out. There's other things you could do, but for the purpose of this, we're just going to take them out. So now we basically just want to apply a Kalman filter in such a way that we can basically predict how fast that he's going to run before every single observation. And this is what you get. So the red line here represents the estimated time that he is expected to run at every observation. And the light red color represents the uncertainty around this. And so you can see at the start of his career, we have quite a lot of uncertainty. That's because we've never seen him run before. So he could literally be very bad or he could be very good. We don't really know. As we see more observations of him, we get more and more certain about how good he is. And the red line, which is the prediction, does a reasonable job of kind of staying in the middle of those green observations, which is kind of what you want. In reality, though, you would want to take other features into consideration, such as the weather, the altitude, the race importance. As you can see, particularly if Usain Bolt, his world record and his two other fastest times, one of which was also a world record, were recorded at the Olympics and the World Championships. So he's obviously kind of saved himself for the big occasion. This is not accounted for here, and that's if you were modeling this properly and we're going to use this for some actual purpose, you definitely want to account for that. But that's kind of how a Kalman filter would work here. So there are a few parameters that come along with the Kalman filter. You would normally optimize them. I haven't done that here, but this is just an example. But they come in the form of a starting expectation. So this is basically, as I said, where that red line starts. So it basically represents the average ability of any runner that might enter the sample. So would roughly be around 10 seconds or a bit higher than that, depending on what your data set looks like. Then you have the starting uncertainty. So that represents the pink light red area at the very start of the sample. Like I said, that kind of represents the range of abilities any runner could particularly run at, a new runner could run at. Then we have measurement noise. So this is basically how much noise there is in each measurement you take. Sprinting, there probably should be like less noise typically, but typically the stuff that we kind of use it for, there is a lot of noise in the measurements. But it basically dictates how much certainty that if you had absolute certainty in any measurement, that red area would basically shrink down to nothing after one measurement. But as you can see, it kind of gets to a point where it kind of becomes quite static, and part of that is because of something called the drift. And the drift is basically how much uncertainty you add back into the rating when you haven't seen someone run for a certain period of time. Effectively, that kind of works as if I haven't seen someone run for one day, I'm adding a bit of extra uncertainty back into their rating. So typically we'd optimize all these parameters just as how you would train any kind of machine learning model. You'd figure out what your metric you're trying to optimize is, which might be mean squared error around the actual observed time. And then you optimize that on a training set and then use it, try it out on a test set. This is one of the biggest benefits of Kalman filters and one of my favorite things to use them for. So Kalman filters are extremely useful and have many applications, including as a rating system. So in this scenario, there would be many teams and players which we are trying to estimate the ability for, and only a small subset of those players are participating in any one observation. So alternatives to Kalman filter here can't really deal with the situations nearly as well. And you can see that by comparing some of the key features that we have here. So ELO, which is probably the most commonly known one, and is famously used in chess rankings all the time, compares very poorly to Kalman filters. And despite that, I see ELO actually used time and time again for these kind of problems. The key differences across them are, so the uncertainty value. So the Kalman filters do have an uncertainty value. So you have a value of their rating effectively, but you also have a confidence interval of how certain you are in that rating as well. ELO doesn't have that. The measurement noise, so how much certainty you have in the measurement. ELO and Glicko is kind of like an extension to ELO, if you don't know. But neither of those assume any measurement noise, which basically means they kind of tend to overfit a bit. Kalman filters, as I've already explained, has that, which is good. And then the updates. This is probably where Kalman filters really shine. Kalman filters maintain a covariance matrix across all of the objects involved, and they won't only re-rate just the objects involved in any measurement. For all alternatives here, that is actually the case. So for example, if player A, let's say you had 3 players, player A, player B, and player C. If player A played player B, you get an observation there, you learn about player A and player B. Player B plays player C, you then also you're still learning about player A because you have a relative rating between B and A. In all these other alternatives, it wouldn't really understand that, and once you've seen the observation, it kind of loses that covariance. But with Kalman filters, that is not the case, and that is where they really shine. So that's it about Kalman filters. So I'll pass you on to Fine now, who's going to talk about how we use them specifically for the NBA and how we're utilizing Databricks.
Thank you. All right, thank you, Bani. Now we have learned everything about Kalman filter. So let us look at how DraftKings leverage like the different kinds of Kalman filters. So at DraftKings, our sport engines are built using Monte Carlo simulation. So we will do one possession at a time. So at one possession, we will simulate different statistics like points, rebounds, and assists. And after the possession, we will check whether the game has ended or not. So if not, then we will repeat the process and simulate one more possession. Now we repeat the process until the game is ended. Then we have finished one simulation. So we continue to repeat the process tens of thousands of times so that we have tens of thousands of simulations. And for each simulation, we get the final outcome of the game. So by doing simulation, we essentially can build a distribution of different outcomes. So imagine like if you want to sketch, if you want to draw a picture of a man shooting a three-pointer, you will first do a sketch and gradually add more and more details to the picture. So it is the same for our own sport engine. So we have a sequence of different models which gradually add more and more details to one possession. So let's say in our model, we have simulated one three-pointer made. So the first question we will ask is that who is shooting the ball? So that means we need to have some sort of probability model to assign the three-pointer to one of the players in the team. And the next question will be like whether the free pointer is assisted or not. So that means we want to have a conditional probability of an assist given a free pointer. So if yes, then we will ask who is passing the ball. Of course, the player who passed the ball will not be the same as the player who shoots the ball, but you get the idea. So that brings us to the Kalman filter. So Kalman filter is the perfect candidate for such a model. So first off, it is very simple. It is essentially just a single number for each team or each player. So we can do a very simple transformation to transform the ratings to probability. So that's very usual. So obviously, Kalman filter is already team and player specific. So that means it is perfect for our use case to generate a player model. So finally, it is very easy to update. We just need, after the game, we just need to do some simple matrix transformation. Then we will have the ratings ready for the next game. So in DraftKings, we try to construct different ratings to quantify different abilities of different players. So we construct ratings to quantify the tendency of the players shooting in different areas. We have ratings about quantifying how often will a player getting a technical foul, or how good a player is in terms of the jump ball. So we believe that we need a lot of different ratings, and there's no single metric that can be used to describe completely the complicated dynamics of a basketball game. So as an example, so one of the measures that we quite often use to quantify how good a point guard is by looking at how good the player is in terms of shooting a three-pointer and versus how good the player is in terms of passing the ball. So obviously, there are players who is good at both of the two things, and they are mostly all-star players. But there are also players who are only good at one, but bad at the other. So infamous Ben Simmons, who is good at playmaking, but quite often reluctant to shoot the ball. So by using different ratings, we have a complete picture of how the player will behave in certain areas. So we now come to the most important section of the talk. We are going to talk about how Databricks transform our workflow. This is a quotation I quite often see in the internet. The most valuable commodity I know of is information. By the same token, the platform which creates and manages information is very valuable to DraftKings as well. Before migrating to Databricks, so we are already using Kalman filter ratings already, but the ratings are trained locally and stored in some local CSV file. So whenever we need to update the ratings, we have to do a deployment, and we have to commit the changes and update the change to production, which is not ideal. So it is particularly not feasible for fast-moving ratings, player ratings. So for player ratings, our perceptions to a player may change quite a lot in a week's time. So we have to have some tasks which updates the rating every day. So this, you can see the screenshot of our local CSV file, but they are not used anymore. So right now, we have migrated to Databricks. We have created workflows to update the data set and update those ratings daily. And after the ratings are updated, there are tasks which send those ratings downstream to our sport engine for calculation. So one of the side benefits of using Databricks is that we can access the history of the tables quite easily. So by using the history of the rating tables, it is quite easy for us to backtest the ratings. This is a very simple illustration of the architecture of the workflows in Databricks. So we have a task which consumes the data from external vendor, and we have rating tasks which creates Kalman filter ratings. And after the ratings are updated, then we will run the feature publisher task to publish the ratings downstream. This is a screenshot of the rating workflow that we have. So the green dots are different tasks which represents different ratings. So currently we have over 200 different ratings, and it will be impossible to manage without a platform like Databricks. So after the ratings are updated, we will run the feature publisher task. So the feature publisher task will read the change data capture table or CDC table. It will figure out which rows have been changed, and the changes are then sent downstream to Kafka. So downstream, we have a service which contains all the information of different players or teams participated in the upcoming game, and it will map the corresponding ratings to that game. And those rating information will be combined with other game information to form calculation requests. And the calculation request will be sent to our sport engine for calculation. This is an advertisement for the other talk. We have some workflows that basically train our models and put it in a model registry. And when the engine is started up, it will grab the latest version of the model from the model registry, and we call that model injection. So unfortunately, the talk has been passed. So if you have a chance, please, maybe you can look up the videos of that talk. That brings us to the model back testing. So the idea is that we can grab one of the particular version of the model in model registry, and for each game in the past, we will get the ratings right before the game starts. So, and then we can run our model to backtest the performance. So by doing so, that we don't have to worry about the data leakage problem because we are not using information from the future to predict the past. So this is a historical dashboard that we built for the traders. So traders can look at the model performance and the outputs and different outputs from the dashboard. So traders can filter based on different criteria, like they might want to only look at star players, or they might only want to look at one particular statistic. So they can even look at just one player and look at the trend of our model performance over time. So one of the beauties of using a Databricks dashboard is that it is quite easy to maintain. So we are completely hands-off, and traders are able to create whatever filters they want or whatever visualizations they want. So we just need to provide them with the data. So now the title of the talk is that how you can make money by betting on the NBA. So we will walk through some of the betting strategy and how you can win money by using the model. So supposedly after the presentation, you should be able to create your own player model. So let's say you go to a bookmaker website and then you see a bet slip like that. So what it means basically is that if you win this, if you bet on the market and if you win, bookmaker will give you back 3.75 times of your stake. So one of the important concepts in betting strategy is expected return. So let's say you run your model and your model suggests that there's 30% chance that you will win. So in this case, the expected return is 30% multiplied by 3.75, which is 1.125. So typically, we will only bet when the expected return is greater than 1. So after we selected the markets to bet on, so it is also equally important that we need to decide how much we want to bet on. So we will suggest you to use the carries criterion. So the idea is that carries criterion will maximize the expected growth rate. So the idea is that every time you will only bet on a portion of your bankroll. So if you imagine that if you always bet 100% of your bankroll, eventually you will lose, and you will lose all of your stake. And at that point, you will see that this strategy gives you like expected growth rate of -infinity. So anyway, so I won't go into the detail of the formula, but you can look it up in Wikipedia. So evaluation is very important for a betting strategy. So ideally, you will have some historical data, and you will backtest your strategy on historical data. And once you start executing your strategy, it is important that you keep track of your profit and loss and see if your strategy is actually winning money or not. One of the tips we can give you is that you only need to bet when you are confident with your prices. So, so let's say you do your bet testing and you find out that your model is only winning when you bet against Steph Curry, and you can only bet against Steph Curry, and your model can be only good at one thing, and you execute a strategy, and you are still able to win money out of your model. So as a bookmaker, we don't have the luxury to choose when we bet. So that means we need to be always confident for all of the markets that we offer. But for bookmaker, we have 2 weapons to have positive hold. So the first weapon is that we are able to control the price. So if we are not confident about the market, we will give you a worse price to bet on, basically, and then you will lose money when bet on those markets. So the second weapon is that we are able to learn from customers' bets. So we are able to identify professional customers. So when professional customers bet on us, then we will adjust our belief on the market, and we are able to give a better price after adjusting from customers' bets. Yeah, and Andy will talk about the summary, and yeah.
Cool. Cheers, Vi. So yeah, just to sum everything up. So we did, in fact, achieve our goal. And over the course of this year's playoffs, we've offered many games throughout on our own internal player prop solution, particularly the finals, Go Celtics. And we are now, as Fai said, we're now producing over 200 separate Kalman filter-based models, which are all producing various different ratings for various players and teams. And all of these models are relying on features engineered through Databricks workflows. Every single model is registered in Databricks, retrained and optimized daily. And this is a huge shift away from where we were a couple of years ago. And these principles have been and will continue to be adopted for every sport that we look after in the sports data science team. So, so if you're interested in hearing more about what the DraftKings engineering team is up to, and specifically our team, the sports data science team, we have a blog on Medium. There's an article on there about Kalman filters, and the MBA, which I wrote a little while ago. If you're interested in learning more, that's it. Thanks for listening, everybody.